All right, welcome everybody. Today we have with us Alex Walley from NCQA as a software engineer, and he's going to cover FHIR in C and C++. Thank you, and maybe a little song, I don't know.
We'll see. Hi everyone, thanks for coming. I know it's a long day, and I appreciate you being here to see some work that I've been doing. A lot of my focus is on the side of my hobbies are working with performance software. So I do a lot of work in C and C++, and I thought I'd give a go, seeing what I can do with FHIR and FHIR tooling. So I am a software engineer at NCQA from upstate New York. I've been there a few years, and I was an intern before that. But I actually have a degree in opera, but I've been programming for a while, from a young age, so I have kind of a mixed I have a mixed background, so it's confusing. I hope I don't need to convince you very much that software performance matters. Not only does it matter from a cost vision for the company, like cloud computing, but it really affects us as developers in the day-to-day experience that we have. And I wanted to share with you potentially a couple screens that I look at every day, and maybe you look at them too. And these are just my tools opening up. Every time I go to work, I open up Visual Studio Code, wait 10 to 15 seconds, then it finally pops up. A little bit later, maybe it'll crash, and I gotta wait another 10, 15 seconds. So these screens really tell me it's a good time for a coffee break rather than starting to program. In terms of FHIR, performance is also important. We can talk a lot about how we want to implement things, but when it comes to actually implementing, performance you have to actually run the code on a computer at the end of the day. So I was interested in looking at that further. You can tell this is an issue because we have groups for this already at FHIR. We have bulk FHIR and the new SQL on FHIR. And a lot of these wouldn't really need to be there if we didn't really care about performance. We could send one patient at a time to the server, but we want a lot to happen quickly. And I firmly believe that reliable and performant tools are critical for the day-to-day experience to decrease frustration, the time you waste waiting for things to compile. If it takes a minute to compile and try to iterate on the next idea, that really wears down, on me at least, throughout the day. So where do I begin when I'm trying to speed up some tooling? If I wanted to create a new basis of tooling where it's all snappy, quick iteration time, so I needed just some way to reason about FHIR resources. How do I talk between the data-oriented approach where the human can understand the resource and the computer can understand? Also, a lot of FHIR programs consume FHIR data more than they produce data. A lot of times you have instances like synthetic patient generation or when you're mapping data initially where you have to produce the FHIR data. But every other tool on top of that, you just consume the FHIR data. And with that, all FHIR data has to be serialized or deserialized at some point in the process. So all of these combined made me realize a great first tool for me to tackle would be a FHIR deserializer. How do I make that the most efficient as possible? And then all other tools built upon that will benefit. So I'll talk a little bit about how I implemented FHIR and a couple of things that are tricky with systems programming. Initially, I started writing all the structures in C++ manually because I'm like, okay, if I have a patient, I look at the spec, I need a name, I need an ID. Quickly that becomes repetitive, error-prone, and not great for future versions of FHIR. So I stumbled upon structure definitions, which do exactly this. It tells me every resource, maybe it inherits from a parent resource, but here are the fields that it has. You might notice that I flattened it into without inheritance. I wanted to keep the data as simple as possible on the base layer, because if you start with more complexity than you need, all tools on top of that are inherently more complex. But you might be wondering, okay, well, it's important that we have this inheritance somewhere. Additionally, C++ doesn't have any metadata, any way built into the language to give metadata. What I mean by that is in C# you can have your attributes for a class signifying extra data on top of the structure. Also in C# you have runtime type information. So at runtime you can say, is this a patient? Do something else. Is this an encounter? XYZ. So combined with the field at the top, which is just an enum of the resource type, that is a struct, I also pulled out a lot of metadata from the structure definitions and put them in another structure and file that I can query when I need that data. So what that means is if at runtime I need to know what type of field is, I can just say, what is the language field on a patient, and I get that information. So at its very core, a deserializer just needs to put data from, usually a file, from one place into memory. So for the ID field, it would go at 8 bytes at an offset. Maybe I'll copy the 24 bytes into 8 bytes in the offset, and then you're good to go. If you see extension, it goes in this spot. So it's really, it's a simple problem, but there's a lot of nuance in there. I'm sure you're wondering, how does it do? How is it? And it's pretty good. I'd say it can be improved, but I've seen some rather decent performance improvements. On the y-axis, you have your megabytes per second. And on the x-axis, I just wanted to show that it's consistent across your data set size. So mine is the blue bars, and then the other two are competing SDKs in other languages. And I made sure that they were the fastest options that the SDK gives me. I don't want to cheat and say, this is fast, but it doesn't do validation, that type of thing. It was tested against files of 50 to 100 kilobytes, one bundle per file. And right now, per core, you can get about 300 megabytes per second. But my machine that I have right now, this laptop, has 24 logical processors, so I can get about 7 gigabytes per second of deserialization speed. I want a couple key things for performance that I found with working with FHIR is, if you remember this process of you have a key to a memory location, if we can speed that up significantly, we already improved our problem. So all keys are known beforehand because we have the structure definitions of every possible key to every memory location. So we don't need to use the generic hash map anymore. We can find better solutions for a static dictionary, basically. And there's a tool called gperf, which generates perfect hash maps where you'll never get any collisions. So it's really just and it's actually an O of 1 lookup rather than kind of like a wavy O of 1 lookup with generic hash maps. Memory allocation. Every time you ask the operating system for memory, it has to shift from ring 3 to ring 0. It has to ask the kernel to give you memory, and then it has to context switch all the way back up. And this can get really slow. So we have the option in C and C++ to use manual memory allocators. I have been using the arena allocator, which is a simple stack allocator or push allocator. If you want more implementation details on how that works, always come up and ask me. I'd love to talk about it. But this basically allows you, when you're deserializing one patient, you allocate a certain amount of memory. When you're done with it, you don't give it back to the operating system, but you just clear it out. So you can reuse it for the next patient. So you skip all of the context switching between the operating system and the user space. Additionally, we can use SIMD instructions. Those are instructions that can do things on a vectorized basis. So I use a SIMD JSON parser, where instead of, if you were parsing JSON, you'd say, okay, curly brace, now we're in a new object, and then quotation, we're starting a string. You can look at those characters, perhaps 8 at a time, 16 at a time. Some SIMD instructions have 512 bits, so whatever that is divided by 8. You can do it that many at a time, and you can really speed up how quickly you ingest this JSON to even reason about it. How do we use this? Of course, you could program in C++ if you'd like. It's not really everybody's thing. So when I'm doing my own tooling with my own SDK, I just include the file, run the deserializer, and we're good. However, at NCQA, we didn't really want to convert a lot of our code bases to C++, because now you need to learn a whole new set of knowledge. So what I did is I implemented a marshaler, which you deserialize with C++, and then you basically map it to FHIR classes. So we can use the speed of C++, map it to FHIR, and then use our existing software on the FHIR classes. And we saw maybe like I think it was a 6x performance. So you lose a little bit of speed in the marshalling process, but you could end up with a net gain in the end. And of course, this could be done with other languages. Python typically just calls into C libraries. You could do the same with Java. Depending on how expensive that marshalling process is, you might see varying returns. But you can use the performance without changing the whole code base. So once I have this, I've done a couple other things. Most recently, I've been working on a view runner with the SQL on FHIR view runner project. And that basically, we can take the FHIR JSON, put it into a format that's great for databases, and we can use existing software, existing SQL software for more efficient lookups, analytics, all that tooling, which is great. If you want to learn more about our specific use cases at NCQA, I'm talking at 10 a.m., 10:15 tomorrow. So what else can you do? I haven't explored this space, but I'd like to in the future. Of course, now that we're in a systems level language, we can explore using embedded systems. And what that means is we can now produce FHIR from the very lowest part of the tech stack all the way up. So there's no reason to have a proprietary format if you have an observation anymore. From the lowest level, you could have a machine, it takes your blood pressure, emits FHIR resources, and then you use that all the way through the tech stack. So now you remove another layer of mapping data. Another thing you could do is compile to WebAssembly. There are a couple of restrictions with WebAssembly, in particular with SIMD instructions, where it limits you to 128-bit SIMD instructions, which have been around for 15 years, maybe more. But this will allow us to use sandboxed native speeds in the web. So now you can build web apps that use the performance of C and C++. That's all I have. You can contact me here on LinkedIn or my email, but I'd love to hear if you have any questions, and feel free to come up afterwards if you have more detailed questions. Thank you.
This is very, very cool stuff. Thanks for showing it. Can you talk a bit more about the marshaler you built? How does that work? So do you start the code from C# and it calls out to C++ and then it returns you a deserialized object?
Sure. So what happens is I bundle the deserializer in a DLL and it puts it in memory. And the marshaler, I generated some code in C# to basically, once it's in memory and you have all the structure, you just read the byte at the byte offset from the struct and put it in the FHIR class. So if we have a patient, it deserializes into memory, and then using the metadata that I have from the structure definitions, I say, here it is in memory, and here is the offset that you want. Copy that and paste it into the FHIR class. So it's a relatively simple process. I wrote some code generation where I have a Marshall patient class where it looks at offset 8 for the identifier, offset 16 for something else, But that's all it is, yeah. Thank you. Any other questions?
All right, thank you.
All right, thank you.